Now we'll use some math to figure out the quantities you have to know to calculate probability. Remember, to calculate the probability of an event, you have to know how many elementary outcomes are in the event, how many elementary outcomes are in the sample space. Sometimes the sample space consists of too many possible elementary outcomes to list them all. Now when that happens, you use counting rules to figure out the size of the sample space. A counting rule, well, that's a formula that allows you to quickly calculate how many elementary outcomes are in a sample space, or in an event. Here's an example of what I mean. Think of all the possible ways to configure an automobile that can have 10 interior colors, 8 exterior colors, 3 transmissions, and 3 body styles. If you had to list them all in order to count them, that would take a while. Here's another example. All possible 5-card poker hands in a 52-card deck. Try writing down all of those. Well, for that automobile example, we apply a counting rule called the product rule. Here's the example again. 10 interior colors, 8 exterior colors, 3 transmissions, and 3 body styles. The number of possible configurations is 10 times 8 times 3 times 3 equals 720. So if all configurations are equally probable, the probability that a buyer selects any particular configuration is 1 over 720, or 0.0014. Many more counting rules are available for us, but before you learn about them, you have to learn about factorials. A factorial counts the amount of sequences you can create from a set of objects. Here's what I mean by a sequence. We have 4 people, Al, Barbara, Carl, and Dawn, and we have 4 adjoining chairs. How many different ways can you seat them in the 4 chairs? Each way is a sequence. Any of the 4 can sit in the first chair, any of the remaining 3 can sit in the second chair, either of the remaining 2 can sit in the third chair, and the last one sits in the fourth. For this example, that's 4 times 3 times 2 times 1 equals 24 possible sequences. For 5 people, it would be 5 times 4 times 3 times 2 times 1, 120 possible sequences. And for 6 people, it's 6 times 5 times 4 times 3 times 2 times 1, 720 possibilities. Each of these is a factorial. The first one is 4 factorial, the second is 5 factorial, and the third is 6 factorial. As you can see, these numbers increase rapidly. That's why mathematicians use the exclamation point as the symbol for a factorial. So 4 factorial is 24, 5 factorial is 120, and 6 factorial is 720. An easy way to define a factorial is that it's the product of an integer, a whole number, and all the integers that are smaller. That means we'll need a definition for 0 factorial, and that's 1. In this spreadsheet, I have factorial, combinations, and permutations. These are topics that we'll discuss in a little while. Right now, we'll concentrate on factorial. So let's look at 52 factorial. We'll find the built-in factorial function in the math and trig formulas. Here it is, fact. And in that number box, we have to enter the cell that holds the number that we want to calculate the factorial of. This is the number in C2. Click on OK, and the answer, a gigantic number, appears in cell D2. Now let's say I also want to know what 5 factorial is, the number that's in C3. You can do that very easily by dragging into D3, and there it is, 120. Now, we can start applying factorials to combinations. Imagine that Al, Barbara, Carl, and Dawn are competing for 3 jobs in a company. And how many ways can the company hire 3 of these 4 people? When we talk about that, we're talking about combinations. Here are the possible combinations. Al, Barbara, and Carl, Al, Barbara, and Dawn, Al, Carl, and Dawn, and Barbara, Carl, and Dawn. That's 4 combinations. Here's another example. Suppose Al, Barbara, Carl, and Dawn are competing for 2 jobs in a company. How many combinations of 2 of these 4 people can the company hire? Well, here are the possible combinations. Al and Barbara, Al and Carl, Al and Dawn, Barbara and Carl, Barbara and Dawn, and Carl and Dawn. That's 6 combinations. Here's the general formula for what we just did. This is the counting rule for calculating how many combinations of R objects you can make out of a set of N objects. NCR is the way statisticians abbreviate that. The number of combinations of N things taken R at a time. That's equal to N factorial divided by R factorial times N minus R factorial. So for the first example of 4 people competing for 3 jobs, That's 4C3, 4 factorial divided by 3 factorial times 1 factorial, which is 4. And for the second example of 4 people competing for 2 jobs, that's 4C2, 4 factorial divided by 2 factorial times 2 factorial, which is 6. Now here's an example for a very large sample space. I hinted at it before. How many 5-card poker hands are possible in a 52-card deck? That would be 52C5. How many combinations of 52 things taken 5 at a time? So that's 52 factorial divided by 5 factorial times 47 factorial, which is equal to 2,598,960. We couldn't list them all, as we did in our first examples. And now we'll take a look at how Excel handles combinations. Once again, we look in Math and Trig for combin. That's the combinations function. The number in cell C2 and the number chosen. That's in cell C3. Click on OK. And there's the 2,598,960. We can apply this to probability. What's the probability of dealing a royal flush? A royal flush is ace, king, queen, jack, and 10 all in one suit. 4 of those are possible. That's the number of elementary outcomes in the event. And the sample space consists of the 2,598,960 possible poker hands. So the probability is 4 over that gigantic number, which is 0.0000015. In combinations, we don't consider the order of the objects. In a permutation, we do. Imagine that Al, Barbara, Carl, and Dawn are applying for 2 jobs. The order of hiring is important. How many possible permutations can we have? That would be 12. And this is the counting rule for calculating how many permutations of R objects you can make out of a set of N objects. It's abbreviated as NPR, the number of permutations of N things taken R at a time. That's N factorial divided by N minus R factorial. For the example that I showed you before, the counting rule yields 12 for our example. 4 factorial divided by 2 factorial, 12 permutations, 4 people taken 3 at a time. Now here's an example for a large sample space. How many 7-character computer passwords are possible if a password can consist of any of the 26 letters of the alphabet, any of the 10 digits 0 through 9, and we can only use each character once with no repetitions? Well, here's what it would look like. Permutations of 36 things taken 7 at a time is 36 factorial divided by 29 factorial, gigantic number. We couldn't list them all, as we did in our preceding example. The probability of randomly stumbling on a correct password is very small indeed. So back to the spreadsheet. Now let's look at permutations. Imagine a poker game in which the order of the cards dealt to you is important. So we're looking at the number of permutations of 52 cards taken 5 at a time. This one is in statistical functions. Permute, the number, 52, is in cell C2. The number chosen, 5, is in cell C3. Click on OK. The answer appears in cell F2. What's the relationship between permutations and combinations? Well, let's just divide the number of permutations by the number of combinations. And that's 120 for this example.